Now I want to talk about two very coupled topics. The first one, I'm going to spend quite a bit of time on this one, is dealing with flexible molecules, and then I'm going to apply that topic to what I view as the most important of spectroscopies, which is NMR. Okay, so let's talk about flexible molecules. Specifically the property. The property of a flexible molecule needs to be calculated as the sum over individual contributions, where the weights of that sum are obtained from the Boltzmann equation. This automatically suggests that there's a temperature dependence and automatically gives you a limit. If you go to zero temperature, you'll have one way of averaging. If you go to very large temperature, you'll have a completely opposite way of averaging. So I have to think about temperature. I'm just going to talk about room temperature. At room temperature, an energy difference of 1 kilocalorie, 4 kilojoules, corresponds to a difference in weights of about a factor of 10. So if you have two conformers that differ by 1 kilojoule, one's going to be 90%, 1 kilocalorie, one's going to be 90%, the other one's going to be 10%. The point I want to make is that small energy differences, just a few kilojoules, are the difference between something being an important contributor and completely unimportant. By the time you get to 8 kilojoules, 2 kilocalories, you're down to about 5%. By the time you get to 3 kilocalories, 12 kilojoules, you're down to about 1%. The point to be made is that the important average is really only those conformers with energies that are below a few kilojoules, 10. Anything else is irrelevant. That seems like it's going to make your life easy, but the problem is, in order to find those few good structures, you really have to look everywhere. And so the problem of treating a flexible molecule is really having to examine everything that's reasonable and then to narrow that down to the things that are important. Okay, it's a difficult problem, actually. Now, what do we know from experiment? Actually, very little. We know a great deal about the conformations that molecules take in the crystal. We have more than 800,000 crystal structures, all of which show molecules in different conformations. And half of them are probably flexible molecules. So we know a great deal about how molecules want to crystallize. We don't know if that crystalline conformer is the same as the conformer in solution or the same as the conformer in the gas. We don't know that. But more important, the crystal data doesn't tell us anything about other conformers. You only crystallize most of the time in one conformer. There are exceptions to that. So we actually, from the data which are most prevalent, crystallography, we know nothing about conformational energetics. So it doesn't help us in establishing Boltzmann weights. We know for some very simple molecules with one conformational degree of freedom, things like butane, we know about energy differences experimentally. There are probably 50 molecules, maybe even fewer, where we actually know the difference between one conformer, trans-butane, and twisted butane, or butadiene trans versus it's actually not cis, it's twisted. There are very few data. So it is rather critical here to establish a computational reference. Since I'm going to be using bigger molecules, I'm going to use G3MP2, and I'll go to one better method for one case, an important case, in a few minutes. So let's look at G3MP2 conformer differences versus experiment, and if I plot those over this is 30 molecules, it's not bad. Now, Are the differences due to the experiment or the calculation? I suspect they're mostly due to the experiment, but the two are clearly related. They're not perfect. I don't have a perfect line. Again, here I'm going to blame the experiment. These are very difficult experiments, especially once you get to energy differences that are more than about 15 or 20 kilojoules, because it's hard to see the other member. In order to measure an equilibrium, you actually have to see both partners. Because these are small molecules, I want to verify that G3MP2 is, in fact, nearly as good as G3. And these are both approximations to that. So here's the easier approximation, here's the harder approximation. And if I plot one against the other, they're perfect. So what it's telling me is that this approximation, I haven't plotted this. I should have shown that slide. It's also perfect. This approximation, which I can do on molecules that are maybe 20 heavy atoms, getting pretty big, is the same as that approximation for this simple case. So now I have a reference. Let me look at some molecules that are bigger than the ones that are available experimentally. So I'm going to go past that. But they still have only a single degree of freedom. For example, cinnamic acid, there are two conformers. There's this one, and you can twist around that bond. Or here's a tetrahydropuran. This has two conformers. One, this is equatorial, and the other one is axial. Okay, so molecules that are a little bigger, but I can do G3MP2, but I don't know experiment. So I'm going to throw experiment away. I'm not going to use it anymore. If you look at that, and you now say, here's my reference, now let's do some practical functionals. Here is the XD functional with a big basis set. This is still much less costly than that. It's not perfect. Here's a XV functional with a big base set. It's not perfect, but you clearly can see that we're reproducing the trends. We're not perfect. So confirmation is in fact not so easy to get, is what I'm trying to tell you. Now, if you look at these relative to the functional that's commonly used, B3-lip, everyone's favorite, B3-lip is terrible. Here are the modern functionals. Here are two of them. They're not perfect, but they're clearly better than that. So this, again, is a set of data where I'm looking at differences between high and low energy conformers restricted to a pretty small range, 15. And you can see that here B3-lip is doing fairly poorly. It turns out that RIMP2 is actually very good. It's actually the best of the batch. Now, that's almost to be expected because G3MP2 is actually, its correlated method is actually MP2. So it's almost to be expected it's the best. But in fact, this method is actually pretty good for confirmation. There's a giant disadvantage to MP2 when we start dealing with confirmation of larger molecules, in that its cost goes from quite modest to very, very much rather quickly. Now, what influences confirmation? What do we know? We have a lot of qualitative information about what things are important, but can we put that quantitatively, and can we see how well individual methods do? I'm going to mention just two factors that influence confirmation. There are several others. One is hydrogen bonding. I'm sorry, this slide's hard to see. The yellow lines are hydrogen bonds. There's actually one mistaken line in one of these. But you can see here's a simple molecule, and each one has different hydrogen bonds in it. This one actually has none. Has one between that's a nitrogen and a hydrogen. This one actually doesn't have any. You can see that as I change confirmation, the hydrogen bonds, hopefully in your printed copy it's showing up better, you can see that the hydrogen bonds are shifting around. And so one of the important interactions that we have to be able to take account of is the difference between one hydrogen bond arrangement and another. Another thing we have to take account of is especially when we get to large molecules, is called pi stacking. Pi systems tend to interact, not always favorably, but arrangements where you have two pi systems that are like this have a different energy than when they're like that. So that's another kind of fundamental interaction. There's a third kind, which I haven't put a slide up, which is pure dispersion. That is that just bulky groups tend to want to get near each other. They tend to want to coalesce rather than sort of fall apart. If you put these in a table, I don't like tables with lots of numbers, but I'm going to do it here. I've got a number of examples of two-molecule systems. So these are interactions. They're not intermolecular, they're intermolecular between two molecules rather than the same molecule. This is easier to demonstrate. There are hydrogen bonding interactions between two waters or between water and pyridine. There are interactions which will come down as pi stacking interactions, pi-pi. There are what are called sigma pi interactions between a polar sigma bond and a pi system. I didn't show those. Then there are dispersive interactions between two hydrocarbons. You can see that they range from hydrogen bonding interactions that become order of 30 kilojoules to fairly small dispersive interactions that are a third of that. And the other ones, sigma pi and pi-pi, are somewhere in between. Okay, if I look at a reference, these turn out to be couple cluster theory, so these are really quite good. They're tiny molecules, so you can actually do it, although this is actually getting pretty big. You can see here, if you walk across the density functional theories, and I've only put the modern ones, you can see that just go down to errors, mean absolute error, and this error is based not on this set, but on a much larger collection. You can see that they're all pretty similar. Some of the methods with the dispersion term, which is analytical, are a little better, but they're all pretty similar, so it's hard to differentiate. And that's going to turn out to be a positive thing, because we're going to have lots of choices in doing that. We have a very few examples of molecules that have many conformations. I've been talking about one conformation, the good conformation, the bad one. We have very few examples where we have very good calculations on molecules with a large number of conformers. The best one that I'm aware of is a series of couple cluster calculations on the conformers of melatonin. This is not a terribly interesting molecule in the sense that it doesn't really have some of the important kinds of interactions, but it's the biggest thing we have. These are extraordinarily expensive. These are weeks of computer time, one conformer, and so someone's done this actually. Okay, this molecule has 5 rotatable single bonds and something like 50 or 60 conformers that are stable. If you look at the difference between these are the overall errors between the reference and different practical methods at 2 basis sets, the limit and this somewhat smaller. So the cost differential here between this column and this column is maybe 10. The cost differential between this column and the reference is probably 100. So the reference. If you look at this, you'll see a couple of conclusions. The first conclusion is that all the functionals, possibly with the exception of the M11 functional, are much better than B3 lip. for confirmations. We already hinted at that with the earlier example I gave, but all the methods are better. For some reason, this one is not as good. I don't know the reason for that, but it's clearly coming out not as good on this one example. The other methods are similar. If you had to pick a best one, it's that one. It's showing an error of, and this one, it's showing error of a half a kilojoule, which is really nothing, a large base set, and a kilojoule, which is also pretty close to nothing on a practical basis. So what this is telling you is based on one example, and one needs more of these. There is some reason to sort of favor that method as the thing to actually finally establish confirmatory differences. Instead of talking about energy, it's maybe useful to talk about Boltzmann weights. So I'm looking at what conformers in this list, in this molecule here. As I said, there are 5 bonds. There are about 50 conformers. Only a few of those contribute. So the best assessment of methods is which few contribute. Here's another table. These are the Boltzmann weights of the top 5 conformers from the reference, and you can see these sum to 90%, 85%, something. They're not 100%, but they're summing to the majority. So this is the reference. If I look at B3 lip, I'm completely off. The lead conformer is different, and so I'm dominated by that one instead of that one. If I look at the other methods, the ordering is much better. The numbers aren't perfect, 61 to even the best of the methods, 70. That's not bad. But so this is a way of judging how well we're doing. Now, I'm spending time in this because if you really want to learn about flexible objects, you really have to be able to have some confidence that the Boltzmann weighting is reasonable. Okay, now I'm going to immediately turn to a real molecule. We've gone from molecules with 2 conformers, where we have some experimental data but not much, to a molecule that has 20 or 30 or 40, and there are a lot of molecules like that. Now, let's just pick something real. Here's a drug called Apollo, and there are about 20,000 structures you can draw. There are 11 rotatable bonds, and if you just do a search, you'll find there are about 20,000 structures. You can't, and this is more common than the ones with 20 structures. I think someone once did this of the many thousands of known pharmaceuticals that are classified. The average number of rotatable bonds is something like 10. So this is closer to what the average is than the few. Okay, how do you deal with this? You can't deal with it in the same way that you deal with a molecule with 20 conformers. You can't just throw the calculation at it and say, do it. When you get to 20,000 or 100,000, you can't do that. So you need to use a multiple step recipe, and we've been playing with this for a long time and slowly coming to good conclusions. The multiple step recipe has to be something like this. Okay, I'm going to repeat this slide a bunch of times. I don't mean to imply there are specific methods with a couple of exceptions. The first exception is the first step is mechanics. You have no choice. And then we're going to have other steps. And the reason for a multiple step recipe is that as we go between steps, we can gradually throw away things. So the idea is the first step is going to consider the 20,000. The next step is going to cut this down to some number. So in principle, we're improving quality. And as we improve quality, we can be a little more we have a little better ability with every improvement in quality in eliminating. And so finally, when we get down to the costly steps, we want to not deal with 20,000, we want to deal with 10. And we want to try to do that in such a way that we haven't thrown away any of the really good ones, the ones that finally contribute. The final result may be 1, but you don't know that. So what the goals are the successes are the following. At the end of mechanics, we can say we don't trust mechanics, but maybe we can trust it to 50 kilojoules. That's a big number. So we can say, look, I don't really believe you, but I'll believe you can separate things that are the good ones, less than 50, of which only a few are going to contribute, from the bad ones. And that actually gets rid of an enormous number. That of the 20,000, that will get rid of all but hundreds. The second step in the recipe is a geometry optimization. I want to replace the mechanics geometry by something better. And the reason for that is that mechanics has the problem of many minima collapsing. So if you have a minimum here, in the real world, mechanics will often collapse it. And so our mechanics searches are actually rather special. They don't allow collapsing. So the second step is a geometry optimization, where at the end of that I'm going to notice that I have lots of duplicates, things that I didn't allow to collapse that all of a sudden have become the same. So we can get rid of duplicates. Third step is to do the first reasonable energy. We have very poor geometries, but we can now do a reasonable energy, and now we can reduce our energy threshold by an enormous number, from 50 down to maybe 15. And what that does is reduce hundreds to tens. And then finally, then we can do an optimization. So I've now done energies. Now I can do an optimization at a good theory. And what that does is gives us more confidence, and we can further reduce our threshold. The idea is very simply to keep lowering the threshold of where we throw things out, and finally, from a start of a giant number, we can finally get down to very few. In practice, there's quite a bit of experience with this now, and in practice, 1,000 conformers for 3-2-1 geometry optimization is practical. Hours or tens of hours of computer time, it's practical. 200 conformers, maybe a few more for the energy calculations, is practical. 50, maybe up to 100 is practical for geometry. And getting down to where we have to do a final energy thing, maybe 20, 30 is practical. Now, when I say practical, I'm really referring to order of, I start with a molecule and maybe I want to spend a day of computer time. Computers are cheap. So if one wants to extend that to a month, you can go further. But this is clearly more costly than doing calculations on single molecules. All this can be automated. The present versions of Spartan partially automated. In about 2 months, we're going to have this completely automated, where we're basically just sort of say go, and it's going to follow a set of rules, and those rules can be changed if you want. Okay, so even though the computer time is significantly more costly than it would be for a single molecule, the actual time in human effort, and I view that as the more important one, is the same. Let's do an example. Start from mechanics. We have to do mechanics. We have no choice. If you were to look at the performance of mechanics in these cases where we have two conformers, so we have conform A and conform B, you look at the reference or experiment versus mechanics, you can see it's pretty crummy. If you ask a slightly easier question, this question is looking at differences in simple molecules. If I ask an easier question about one molecule differences, so let me go back to my melatonin example. Here you can see this is the conference of melatonin, so there are 50 something, and this is the reference, which is very good theory, versus MMFF. You can see that we've got a trend, and you could probably see that I could trust this up to some number, maybe 20, 30, 40 kilojoules. So we have no choice but to use mechanics as the initial filter. There is a reason to try to develop better methods. But let me just make a comment. When you do a conformational search, there are two possible objectives. If you want to find a Boltzmann distribution, all the good ones, you have to do a systematic search. You have really no choice. The alternative is if you want to only find the best conformer. In that case, you can do something called Monte Carlo searching, which is something that's been emphasized for a long time. There, you will rapidly find the best one, but you will rapidly ignore other regions which might have other good ones. And so for the purpose of finding the best one, Monte Carlo methods are fine. For the purpose of actually trying to get a good distribution, Monte Carlo methods are not acceptable. I always show this slide to show you the advantage of Monte Carlo theory when you can use it. This is one of the statin drugs, and there are about 4,000 conformers of this drug. So it's typical, it's smallish. If you want to find the best one with systematic, you have to look at all 4,000. If, on the other hand, you do Monte Carlo theory, you will find the best one in 200 steps, about 5%. And you'll actually come extremely close within 100 steps. But I do want to emphasize that if the objective is to establish Boltzmann, which is really what I'm talking about, then you really have to look everywhere. Second step and the third one, we now have a list of good conformers. So this list is going to be hundreds. So I've thrown away things that are high energy. The next steps, I'll consider them together: structure optimization, and then do an energy calculation. So this, for the first time, gives you an energy estimate, which is fairly reliable or maybe fairly representative. And what we've discovered is that it's not perfect. So let me give you a couple of examples. I'm going to use two very simple molecules, and I'm going to show you only a few conformers. The two are withdrawal. This is a plot of what my final result energy is. So I haven't gotten there yet, but I'm jumping ahead, versus the energy at this step. So this is my final result. This is actually the red line is actually what I'm going to get at the end. And at this cutoff step, where I've used a simple functional and a very simple geometry, you can see now there is a pretty decent relationship. And in this case, we could probably easily draw a line at 15 or 20 kilojoules and say, throw away these. Here's another molecule, haloperidol, and again I'm showing only a certain set. You can see here it's not perfect again, but you could probably successfully throw away that zone. You probably throw away half at that point. So this is the first step where we have an energy estimate that we can begin to believe. We can't use this to get Boltzmann weights, but we can use it to get rid of things. So going back down, the last step is to pick some density functional method that we can trust. Here I can't show you truth, but what I can show you is my final result, and I can show you this with different functionals. So this is one functional versus another one. The fact that they're similar is consistent with our previous behavior when we talked about where we actually did know the limits. So we've reached a point where the functionals, these are similar. We've reached a point where we can say we've probably converged. So we're getting down to the point where we can probably say that the result we're getting is not going to change significantly as we go to better and better. This is the point where I'm saying you can probably calculate a Boltzmann average without worrying about it too much. Again, I just want to emphasize that we're getting down to the point where we can really say that the results are virtually identical as we change from one functional to another.